Cool. All right, let's get started. It's 12:18, so we got, I think, everyone here. All right, so for the last time, if you haven't been here before, my name is Jorge. Graduated from Queens College in January. Software engineer at Google, starting in 19 days, I think, at this point. So super excited. We're going to be doing our last workshop at Queens College, since I'm obviously not going to be here anymore. I'm going to be in Massachusetts for the next year and a half or so. So this would be our last part. And honestly, is the most important part to end on, because when I did my interviews for Google, all 5 of my technical interviews were graphs. So it's really an important topic. If you were here for last week for trees, or 2 weeks ago, I guess it was, good, because trees are just graphs that are acyclic and directed and have n-1 edges. So it's like a very specific type of graph. So if you understand trees, that's good foundations for just generic graphs. Because in the end, like I said, trees are just a specific type of graph. So if you understand trees, if you understand even linked lists, that's also a graph, right? So we're gonna do like real big boy graphs this time. So raise your hand if you've never done graphs before. If you've never done it, like, be honest, it's okay. I actually never did graphs until like August, and like I had to like learn it in a month. Cool, so it's fine. The graphs are honestly something I don't think they teach you here at QC. I did not learn graph algorithms at all. At least I don't remember. I did do some graph stuff when I took AI's class with Dr. Greg, but not in like my data structures or algorithms class. I think we stopped at like trees and like other stuff like that. So it is more of an advanced thing. So definitely you want to spend some time focusing on this, since honestly, if you can do graph problems, you can probably do anything else on LeetCode, because graphs incorporate arrays in matrices. They incorporate pointers in trees, right? They incorporate hash maps with adjacency lists, and they incorporate depth first search, breadth first search. They incorporate everything. So everything you've learned in basically from workshop 1, 2, 3, as well as like your foundations, apply here. So it's actually a really good thing, bang for your buck. All right. So let's just get started. And I'm going to give you just like a little bit of quick overview, and then we're going to do some problems, because I want to make sure everyone's on the same page. All right. So I'm going to give you an example of a graph. All right. So this is a graph. What type of graph is this specifically? Pop quiz if you were here last time. Yes. It's a binary tree, or it could be just any tree, right? Another version of a graph could be something like this, right? So this is a tree with 4 children, right? And then you can do whatever you want. That's the thing about graphs. You can do whatever you want. So here's a tree, right, with just multiple children. This is called an n-array tree, but it's a graph, right? You got your vertex, right? This is like a vocabulary word, vertex, your nodes, and your edges, which is like the things that connects them. Also specifically, you notice that this is an arrow pointing into a certain direction. That means it's a directed graph. It's a directed edge. So this node only points to this, and you can't go back to this node. Does that make sense? That's a directed graph. If I wanted to make this like an undirected graph, which is another different thing that you have to know, it would just be removing the arrow and instead pointing a line. Does that make sense? So we are going to have directed graphs and undirected graphs. The cool thing about graphs is you can do whatever you want. There's no specific constraints, which is what makes it harder, because there's not like trees. We just know n-1 edges, they're directed only from top to down, and they have 2 kids if it's a binary tree. So it's very constrained. This is not. An example of a graph could be like your Facebook social network or Instagram followers, right? You have your name on Instagram, and then you're pointing to people that you follow, and they might always follow you back, and you can create a whole graph of people that you follow on Instagram. As just an example. Another really important graph is the MTA map. You can actually, this is a graph if you really think about it, right? Because you got your nodes, which are the actual subway stops, right? The edges between connecting the nodes. And you can actually do some like CSCI sciencey stuff with like data analysis using subway stations, because it is a graph. Specifically, it's a undirected graph, because this station goes to this station and you can go back. You can go from 82nd to 74 and 74 to 82nd, unless like there's some maintenance going on, right? So graphs are everywhere, and they're in almost everything you can think of. So it's a very, very useful thing. So here's an example of a graph that's more generic. So I'm going to draw a graph here and then go here. All right, here we have a graph. It's going to be an undirected graph because there's no arrows. Let's give these a bit of a label. So let's call this 1. Oh my god. Make this a little bit less thick. There we go. 1, right? Let's call this node 2, node 3, node 4, node 5. I'm just arbitrarily labeling them, right? So let's talk about this. Node 1 is connected to node 2, 3, and 5, right? And what happens if you go here? 1, 2, 3, we can go back to 1. So what is this called in a graph when you can do this? Does anyone know like the vocabulary word? Cycle. It's a cycle. We can go in a cycle forever. All right, that's something that you need to remember. In graphs, we might have cycles, and you have to be able to identify them. And no, we're going to do lots of this like in actual coding in a second. Here's another example of a cycle. What did I just do here? What's happening over here? 2 can go to 2, and it can go to 2, and it can go to 2. That's a self cycle, also a cycle. So that's also a valid graph. Everything here is valid. Things that we can do with this graph. What is the shortest path between 1 and 4? Can someone tell me? Any shortest path. It could be a shortest path. 1, 3, 4. So that's how many steps? 2 steps, right? Step 1, step 2. Another shortest path could be 1, 5, 4, right? So that's the shortest path. We found that. Another question could be, how many paths can we take to get to 4? Unique paths. Right, we got 1, 5, 4. You got 1, 3, 4. You got 1, 2, 3, 4. And that's all, right? Unique paths. So like without cycles, you don't want to go like 1, 2, 3, 1, 5, 4, and then like that's just going to be unlimited. You're not going to ever find you're not going to have a finite set of paths, because if you can just say, oh, I can just do this 100 times, like that's a unique path. That's not. So unique paths, we have those, right? So we count paths. We can tell you shortest path. We can also test if a path exists. So here's another example of a graph. So here's a node. Let's call this 6. Is there a valid path between 1 and 6? No, it's not connected. Is there a valid path between any of these nodes and 6? No. In discrete math, we call it a disjoint set, because 6 is disjoint from this graph. So another question could be asked, determine if a path exists from node 1 to 6, given a graph, right? So from there, you can search, and you can realize, oh, I've searched this whole graph, right? And yet there's still not 6. Therefore, 6 doesn't exist in our graph, right? That's another type of graph algorithm. And again, we're just doing conceptual. I'm not going to no code. But do we all kind of understand like the concept of what we're doing right now? Any questions at all about just this basic idea? Cool. So you should all be at this point just kind of familiar with how it works. And basically that's all there is to it. It's just those are the most common questions. Find shortest path, find number of paths, find if you can find a connection between those nodes, and just variations on that. Let's see. And then to search these graphs, how do you search them, right? There are 2 main algorithms that we need to know. There are more extensions of those, but the 2 main algorithms you need to know are depth first search and breadth first search. So in trees, we kind of talked about it before, right? So let me just kind of scroll over. So like just quickly make an ugly drawing. For trees, let me just make a little tree. Here's a tree, right? So easy peasy tree. Oh my God. Cool. All right, here's a tree. Depth first search, right, is we go as deep as possible, and then we return. So for example, in order to be go as far left, then a root, then far right. So it'd be like this node first, this node first, this node first, as deep as you can, then this node, and then we're done. Right? That's DFS we talked about last time. BFS would be this node searched here, then these 2 nodes are searched, and these 2 nodes are searched. Right? Just as a review, we're going to go over it for graphs, but the same exact thing applies for graphs. We can do depth first search and breadth first search. So how would that work? Well, let's kind of draw it out. So depth first search could be something like this. You start at 1, right? And let's just I guess find a number of paths to 4, right? And let's just greedily go from arbitrarily from lowest numbers to largest to highest, based on where it's connected to. So the lowest number is 2, so let's go to 2 first. So we go as deep as possible. 2 has no other paths, so we're going to go here, and we're going to go here, and we find a path, right? And then that's one path. And then we're going to go, the next number would be 3, so we go here, then we go here, that's another path. And then we're going to go here, then we're going to go here, that's a third path. But do you see how I'm doing this like one by one, right? That's depth first search, okay? And now breadth first search is going to be something like this. So we're starting from here, step 1, right? And now we're going to expand here, here, and here at the same time. That's step 2, right? And then we found step 3 goes here. We found 2 paths right here, right? And this one's going here still. And then these 2 are done, but then we have one more, and we found the 4th path, right? So that's breadth first search. We're kind of doing it level by level. And also notice that by doing breadth first search, shortest path kind of came naturally, right? So again, we start from beginning, level 1, then we go here, right? And then we're looking, our goal is 4. So step 1 is we got to 2, 3, and 5. Step 2 would be 2 to 3, 3 to 4, which is a goal, and 5 to 4, which is also a goal. So how many steps was that? 2. The shortest path was 2. We already determined that it's guaranteed. We know what it's 2. At this point, 2 to 3, 3 to 4, that is a valid path, but it's not the shortest path, right? Because we already reached it. So another hint, right? Shortest path, think BFS. It kind of makes more sense. DFS can guarantee you a path because it could be here, but it's not guaranteed to be the shortest path. BFS will always give you the shortest path because we're going level by level. Level 2, level 2, level 2, and then level 3, it goes here, and that would be it, right? Any questions on those 2 like traversals that we did like in concept? No questions? All right. So you kind of can understand at this point like how a graph looks like, and just like hopefully you all have an understanding of how it feels like visually, right? This isn't too hard stuff. I feel like if you've done 220, I feel like this is, you've probably seen stuff like this before. Coding it up is a little bit, it's actually fairly standard as well. It's like basically once you get used to it, it's almost like writing a for loop because it's basically the same algorithm every time. But how do we represent these graphs? Let's talk about that first, right? So right now I'm showing you a picture, and this makes a lot of sense. But how can we actually portray this graph in a computer? So there are multiple versions of portraying a graph. And I'm going to show you first the one that I'm going to use for this problem. It's called an adjacency list. So it's going to be an adjacency list, right? It's going to be a hash map or a dictionary in Python. And see if you can kind of catch on what I'm doing. So 1 is connected to 2, 3, and 5, right? 2 is connected to 1, 2, and 3. 3 is connected to 1, 2, and 4. 4 is connected to 3 and 5. And 5 is connected to 1 and 4. Right? Does this make sense? What am I doing here? Can someone explain? Yeah, what's up? Exactly. So to portray this graph, we have the adjacency list. Keys are the vertices, right? So each vertex is there. And also, sorry, I forgot one important one. 6 connected to nothing, right? So we have, the key is the vertex, 1, 2, 3, 4, 5, 6, right? And we have a list as the value. So the hash map is going to have a integer, in this case, as the key, and a list as the value. And the list contains all of the adjacent nodes. So 1 is connected to 2, 3, and 5. You see that visually, right? 2 is equal to 1, 2, 3. 3 is equal to 1, 2, 4, and so on, right? And 6 is connected to nothing, so it's by itself. But it still exists in our list. Does that make sense? Any questions on the adjacency list? This is the easiest way for us to deal with problems. So let's focus on that first. So there are other ways that we're going to do it. Sometimes you have to even build your own list, which I'll explain right after that. But for now, let's deal with this. This is the easiest way. So, question: find the shortest path from 1 to 4. That's your question for LeetCode, right? So let's do that manually. I'm going to run through the algorithm, and you kind of draw it up so you can kind of see it before we code out something like that. So if you want to do, so shortest path, that's a keyword. What algorithm do you use? Breadth first search. Why? Because it's level by level. So once we get to the goal, that's going to be our shortest path. So let's do that. So we're starting from 1, right? So we're gonna also secretly we're gonna have a queue, right? We're gonna add 1 to our queue, and it's gonna be our search thing, right? We're gonna add its children or its neighbors, which is 2, 3, 5, right? 2, 3, 5, right, to our queue. And then we're gonna pop 1, right? So once 1 is popped, so let me just kind of cross that out, right? So now our queue is 2, 3, 5. All right. So at this point, we've searched 1, and now we're going to the next level. So now we're going to be in 2. Let's try 2, right? So we're going to pop 2, add its children, which is going to be also forgot to mention what happens if I add 1 back to the queue because it's a neighbor of 2, but we already saw it. It'd be a cycle. Yeah, I almost messed up. We have to have 2 things. We need to have a queue, which I'll explain more when in the text. But basically, we're queuing up, so we do everything level by level, and we also need to make sure we detect cycles. So, what's a way that we can do? What's something that we can use to help us so we don't like end up searching things in cycles? Hash map, yes, technically. There's a little bit easier thing than hash map. What's a similar thing that's like you can use a set exactly. Use a set. I forgot about that. So let's add 1 to our set, and let's add 2 to our set, right? So at that point, we can check, right? Is our current node in our visited set? If it is, then we skip it. If it's not, then let's keep adding it and searching it, right? So we search 1 and 2, right? And let's say our current level is now 1. So we searched 1 step, and now we're still at 1. So let's add 3. 3 is connected to 1, 2, and 4. 1 and 2 are in our visited set, so we don't have to worry about that. So let's add 4 because that's the only one we can add, right? From there, so we now add 3 to our visited set, right? And then 4, we have 3 and 5. 3 is in our visited set, so we don't add that. And 5 is already added as well to our set that we're in our queue, so we don't really add that as well. So at this point, and also we would technically add this already in our visited just to like avoid all of those problems in the algorithm. So once you see it, like you just add it there. So from there, we're here, right? And we just search it, and eventually we realize, oh yeah, when we first saw 4 at all was step 2, and then we'd stop there. So we only have to continue going, but like if you want to search it, you'd search 5, you'd search 4, and there's nothing there because we already see everything, and the queue would be empty. So then we exit out of the queue, we're done, right? So any questions on like the theoretical idea of how it works, and then I'm gonna show you the code. No questions? All right, so let's do that. Let's do this coding wise. So let me just erase all of this. Oopsie, not the JCC list. So the code is actually very boilerplate. Something that I did because I didn't know what graphs were until like I did my Google interviews. I was bad. I didn't study, so I had to really cram them. And I found that it's basically a template that you can kind of memorize, and you just have to. What I did was I opened up Google Docs and just typed in the algorithm word by word like 10 times until I memorized it. That kind of worked out. So let's do that. So we're gonna have a BFS function. We're doing this obviously in Python because Python is the only language we'd ever do LeetCode in. We're taking in a JSON list, right? And we're gonna return an integer, right, which is gonna be the shortest path, right? So let's do that. So first steps is we need a queue, which is gonna be a delimited queue in Python, right? And then from there, we're going to say, so say we start from 1, right? So let's add this into here. It could be like adjacency list 1, right? So, 0, sorry. So we're adding the first thing in our adjacency list. Well, actually, no, we don't even need that. I'm sorry, my bad. We had 0, 1. That's actually first node. We're just checking node 1. Let me just erase this. There we go. That's all you have to do. My bad. Um, so we're just starting from node 1, right? We're starting from 1, and it's going to be our queue. Let's have a visited set is equal to set, empty set. What else do we need? That's it. Let's start. So while queue exists, that means right now we have a queue. Also, yeah, we need a level. Level is equal to 0, right? Uh, let's go here. Let's say while queue exists, another just boilerplate cheat code is if you want to guarantee that you're processing things level by level, you have to have a little for loop in there, and it's not going to add anything to your time complexity, but it's just gonna you'll see why in a second. So it's just for underscore in range of length of queue, right? Just for now, just trust me on this. I'll explain again why in a second. But it's because of the level, right? So while queue exists, current is equal to queue dot pop left. So what that means is, remember we have our queue, which is an array. We pull from the left side of the array because it's like, you're in the line to buy pizza at Gino's. The person in front of the line gets the pizza first before the person in the back of the line. All right. If cur in visit, return, sorry, not return, continue. So if current is in visit, continue. That's our base case, right? If we've seen it before, we continue. We just move on to the next one. So we will pop the next one. Afterwards, you do this. If current is equal to, oh no, say target. Is current equal to target? You can say level plus equals 1, return level, and just break out easily. But you don't even need to do that, right? But that could just be it. That's like your case of like it's correct. Afterwards, you're just going to say for neighbor in adjacency list of current, queue to append neighbor. So what we're doing is what we did before, right? So say we had our list over here, right? We're at 1. Our goal is 4. We visited 1. So let me also add that as well. Did I add that? I did not. Continue visit that add cur over here. Basically, right, we're at 1. We check, is it in visit? No. So we're going to add it to visit. And then if it is our target, which is not, we return, but we're not. So we're going to just add 2, 3, and 4 to our queue, right? And then afterwards, we finish this step. Then we're going to go to 2. Again, check, is it the target? No. Then is it in visit? No. So we're going to add all of this, right? And keep going. And then from here, after we added the neighbors to adjacency list, we're going to exit the top for loop, right? And just say level plus equals 1. And then I think it's just here, return level. Or actually, you can just do this. Yeah, it's fine. So that's basically like almost like, I'm sure there might be like a little bug here and there because I'm just doing this from memory, but it's very similar, right? Your goal is very, very standard. You have your BFS, you have your queue, you add the first node to your queue because you need to initialize it, right? And this is expecting there's at least 1 node. As an edge case, you could always just say, if, for example, in the edge case in LeetCode, you can say if not adjacency list, return -1 or something, right? If it's like if there's nothing there, as the edge case is empty, you can just, I don't know, deal with it. But you start with the queue, you have a visit set, start with your level, you have a queue that's going to keep going, right, until you search everything. This will not stop until you search the whole graph. Then this for loop is here. The only reason why it's here is because the way this works is that this for loop, the length of the queue is snapshotted. So if, for example, we're at level 2 and we have like 4 things in our queue right now, we're going to only do this 4 times, and that's going to guarantee that over here we know when the level is done, so it goes to level 3 afterwards. Does that kind of make sense? Right, so that's just like the little trick. You need to add a for loop for that. But again, just pull up from the queue. If it's visited, you skip it, or else you add it to your visit. If the current is target, right, you're done. Make sure you return a level +1 because we started from 0. Return level, and then for each neighbor in the adjacency list, append to your queue, add level, and then return level. Any questions on this sort of like idea? This is a bit of a longer, it is a bit of a longer algorithm, but you kind of just have to memorize it. You just got to sit there in Google Docs, type it out 10 times, close your eyes, go to bed, do it again the next morning, type it out 10 times. Eventually, you should be able to regurgitate it in your sleep. That's the goal. It is longer, but it's like maybe 15, 20 lines of code. I think you can memorize 15, 20 lines of code. Great. Any questions on this so far? Okay. And so let's start with that. Here's a LeetCode problem, and I'm going to kind of walk you through it. Right? So here's the problem. Let me actually just copy this. And we're going to do it in a little thing over here. So let me just go over here, add a little text box. Oh Lord. That's not going to work. Okay, just kidding. Let's just read this question. All right. So here's a very good introduction to adjacency list LeetCode problems. It's called Keys and Rooms, 841. It's a medium problem, but honestly, I think it's kind of an easy. So the question's here. You have n rooms labeled from 0 to n minus 1, and all the rooms are locked except for room 0. Your goal is to visit all the rooms. However, you cannot enter a locked room without having its key. So when you visit a room, you're going to find just lots of keys in it. So maybe you just walk in here and just like keys on the table, right? And then each key has a number of the room, and you can take them all with you. So given that, can you visit all the rooms? So example could be, this is room 0. We start from here, right? And then I have keys to over here, say, I don't know, just going to arbitrarily say room 0, I have keys to room 1 and 2, right? So I'm going to go to room 1 and say room 1, there's a key to room 3, right? So I got the key to room 3. And then I go to room 2 and there's a key to room 4. So I got room 4 and say it's only 0 to 4. I visited all the rooms, we return true. However, what if there was a room 5, but I ended up at room 4 and I don't have the key to room 5 after searching all the other rooms? Can I visit all the rooms? No, that would be false. Does that make sense? So that's the question that we're asked. So let me just kind of draw that for you. So given a room, right? Let's just kind of, I'll make it simple, easy cases. And another thing is when you're interviewing for companies like, for example, Google, they're not going to give you test cases. You have to come up with your own. So let's make up our own as well. So here is room 0. And let's say in here it has the key. Let's call this room 0, right? Let's call this room 1. Let's call this room 2. Call this room 3. So let's say room 0 has the key to room 1. And then room 1 has the key to room 3. Room 3 has the key to room 2. And room 2 has nothing in there. So how would this look in a graph? Well, 0 is connected to 1. So it would look something like this, right? 1 is connected to 3, so it would look something like this. And 3 will be connected to 2, which is like this. So that's our graph, right? But you don't even need that because we have an adjacency list built into this. So what if we had more rooms? So let's look at that. So say we had room 4 and room 5. Right? So 4, 4, and then 5. And let's say, oh no, 1 has 4 and 1 has 5. Right? So then it would look something like this. Let me just kind of draw it out. So 1, so here, it's going to be here, it's going to be here, 1's here, here. Bit of a messy graph. But you notice how like it's getting kind of crazy. So for now, we can just think of it as an adjacency list. 0 connected to 1, 4, 5, like that. Does all make sense? Like the idea of how it's working? So we can use that. And basically, what's our goal? How do we know that we've accomplished our goal and then we return true? What's our winning condition here? Hey, what's up? You can get to every single room. Exactly. So I can kind of check this. So check room 0, check. Room 1, check, right? Room 3, check. Room 2, check. Room 4, check. Room 5, check, right? So we were able to visit all the rooms. If we say had, some room 8 over here, we can't visit that. So this would not be checked. So therefore, since they're not all checked, we return false. Does that make sense? Okay. So what algorithm can we use for this? What algorithm can we use? Should we go as deep as possible? Do we go as wide as possible? Depth first search, breadth first search, does it matter? Is there a preference? Is there a reason why to choose one or the other? It's just saying, the question is just saying, can we see all the rooms? So I'm asking you guys, which one should we use? Does it matter? Do we use one? DFS, BFS? Recursive, iterative? Someone said DFS? Who said DFS? You? Why DFS? So is BFS. Yeah. Mm-hmm. 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 Yeah, no, yeah, he's on the right point. So he said we're going to use a set. And he answers yes, you want to have a visited set, obviously, to avoid cycles. But also, what happens if the length of the set is equal to the amount of rooms? A visited set. What does that mean? That means we've seen all the rooms. If the length of the visited set is not equal to the number of rooms we haven't visited all the rooms, therefore we return false. That makes sense? And as for DFS or BFS, it doesn't matter. DFS or BFS, if you don't have like a specific condition, like find the shortest path, you need to use BFS for that. It's a lot more efficient. If you want to do find any path, you can use DFS or BFS. If you want to say find just see if we can see everything, it doesn't matter. Because either way, if you just do DFS over and over and over again, you don't have like an exit condition. You just stop until you're done searching. It doesn't matter because you're going to search anyways. If you have BFS, it doesn't matter if you're just going to keep searching until you're done, right? So don't worry about which algorithm to use. You can actually use both, and I actually recommend for this when we're going to do both because I did this. This is my first like ever JSON list problem. I did this in BFS. I did this DFS iteratively using a stack, and I used DFS recursively. So you can do all three. So we're going to do that just to kind of give you a crash course on all three. So we understand the problem, right? So let me just kind of bring up my solution a little bit, right? Just to kind of save time and also give you the right thing because I don't want to mess up live. So first step, right? We're going to initialize the visit set. So we're going to have a visit set, and we're going to use that to make sure we've seen all the rooms, right? And then we're just going to call our function BFS DFS, and that should kind of do everything for it. And we're just going to return the length of the set. The visit set is equal to length of the rooms. That's a Boolean expression, right? If this is true, it's going to return true. If it's false, it's going to return false. Do we all understand, like on a high level, right? We have a visit set. We're going to call BFS on it, search everything, and if we've searched everything, we're good to go, right? Any questions on that part? Yes.
Is there a case where, say, we have like keys, like if there's a key, we assume that room also exists. We get a key
So in the question you're given like the n rooms.
okay.
So it's yeah, that's a good question actually. So in the actual question, you're given n. So rooms you see over here is given rooms. So your rooms is actually a list of a list, but you can consider it like an JCC list basically. So if the length of this JCC list, that's the amount of rooms, right? Make sense? So that's what we're doing over there. So that's a good question. That's just like the input that we're given. All right. So let's look at the code. Here is a recursive DFS. What's our base case? First, we take in the rooms, obviously, and we take in our current room. Base case, if it's visited, we'll return. We don't want to go into cycles. So that's just base case. Or else we're going to add the room to our visited set. And then for each room in the adjacency list for that specific room, we're going to just DFS those rooms. And that's the recursive solution. It's like 5 lines of code. It's not too bad. So what that looks like in your drawing, right, is like, for example, you go from 0 to 1, and let's go deep, right? So we're gonna go deep into one path. So we're gonna go 1, and then 3, and then 2. So you see how we went over here. Let me make a different color actually. So it's 1, 3, 2, right? And now we're gonna go to 4, 4, then we're gonna go to 5, 5, and then we kind of go from there. So we're just doing that, going as deep as we can to one direction. All right, any questions on recursive DFS? This is as basic as you can get for DFS. So if you can memorize these 5 lines of code, that's like the basic template. Right? No question on that? So let's look at BFS. So BFS, again, is more involved because you're doing this manually. So I asked this last time. What does the recursive version do for us? Like, what data structure does recursion actually use to solve its recursiveness? Does anyone know? This is like a 111 question, but they don't really tell you this. Yeah, uses a stack. So recursion automatically uses something called the call stack. If you should have either learned this in 111, or if not, then I recommend you look a video on it. It's actually really interesting. So recursion uses a stack under the hood. So every time you're adding or doing DFS, you're actually adding this to your stack, and your compiler is kind of doing it for you using a stack and solving it. It's actually not rocket science. Recursion is just a stack. In case you didn't know. So all it's doing is just adding, it's making it a little bit easier. For BFS, um, and if you want to use iterative for this, just become a stack if you want to use DFS. But we have our queue, right? We're starting from room 0, and then while queue means that while the queue exists, while we still have more room to explore, it's just pop left. And again, base case. If the room is in the visited set, continue. That's basically the same thing as the recursive. And then you're going to add the room to your visited, and for room and rooms, add it to your queue. So if you kind of look at both of these problems, like it's basically, let me see if I can kind of fit both in your same screen. So let me see. Hopefully you can all kind of see this, right? It's a little small, but the biggest difference is this part. While queue and queue double in the queue and pop left, this is done for you in recursion. So this is like built into recursion. That's why it's a little easier. And also, here instead of appending, you're just doing the recursive call, and instead of return, you continue. That's the only difference between recursion and iterative for BFS and DFS. And let me also tell you, what's the difference between BFS and DFS iteratively? What do you see? We have a queue equals pop left. If we do q.pop, now we're doing DFS. Because now, what are we doing when we pop from the right instead of the left? What data structure are we using? It's not a queue anymore. So it's a stack. When you pop from the right, it's a stack. When you pop from the left, it's a queue. Double in the queue with Python, you can use that data structure for both. It's actually a double linked list under the hood. So if you pop right, it's a queue, it's a stack. If you pop left, it's a queue. And just by changing that pop left into pop, you're doing DFS now. So this is the iterative solution for DFS. So now these are both DFS. This is DFS and this is DFS, and you're getting the exact same algorithm, but this is just doing it iteratively. Which one's better? Typically, iterative is better because of just recursion causing issues in like some large scale numbers stuff. But for LeetCode and for interviews, either one's fine. Any questions on this problem? No questions at all? Everyone's good? You're all good with JCC lists? Do lots of these problems. It's really just a matter of like spitting out this algorithm, and like when you're doing these problems with JCC lists, which are the most commonly good problems for graphs, and what I got for most of my Google problems, you just want to read the question and say, all right, how do I modify this question to fit my template of BFS and DFS? So you memorize this template. This is like the most basic version of the template with no extra frills or anything added to it. So this is like the most fundamental. Just memorize this. You might have to add some more if cases for like the other graphs. You might have to add some more if other was stuff for like the question that they're asking you. You might have to return early if you need to, but this is going to be what you do. So how can I fit the question to fit my template? That's all you have to figure out. And if you can solve that, you solve the problem, and now you have a job at Google. I'm not even kidding because that's all I did. It wasn't that bad. All right. So we're good on JC's list. As an aside, just to kind of give you a more advanced thing about that, sometimes they don't give you an adjacency list as is. They're going to give you something called a list of edges. So for example, say we have 0, 1, right? 0, 4, 0, 4, 4, and just 0, 5. And then just gonna do one more, 1, 3, right? So right now, what am I doing with this little text over here? I'm saying this. Between 0, there's an edge in 1, right? Between 0, there's an edge in 4, right? Between 0 is an edge in 5. And between 1 is an edge in 3, right? That's all I'm doing. So when you're given a list of edges, you can't really run DFS or BFS on this. You have to convert this into an adjacency list. So how you do that is just manually sometimes some problems will say this. You have to just make your own JSON list equal to a hash map, and you say for, I guess I think it's like UV and edges, and this is called like edges, right? Um, edges like whatever. I'm just kind of giving you like the pseudocode, right? JCC list u dot append v, and if it's undirected, then you say JCC list v dot append u, and this would be actually in Python we can use default dictionary of lists, so we don't have to deal with like extra stuff. Basically, it's saying it's a hash map with lists as the default value. So it's kind of like how you'd make your own. So if it doesn't give you the actual JCC list, you do something like this, and you create your JCC list manually. So some questions will have you create this manually, and you'll get a hint if it says you are given edges. So that's just all you have to do. If it's undirected, you do it for both, or else you'd be something like if u connects to v somehow, right? To v, then you do this, and then you say if v connects to u somehow, you do that. That's the only difference for directed graphs, right? Clear? Okay. All right, let me show you the other example of graphs that you are going to deal with. It's called matrices. So if you've taken 111, you've done 2D arrays, right? And this is just a 2D array. So here's a very, very popular problem. Fun fact, this is actually my second Google interview problem, but it was just like given as a twist. So it was like almost the same exact question, but like slightly different. They don't give you LeetCode questions, they give you variations on them. So I legitimately got this question, and it wasn't easy. It was the freest question I've ever had in my life. So here's a question. Actually, I'll even explain it without even reading the question. So think of this: you're on Microsoft Paint, right, or any other paint tool. Have you ever heard of like the paint bucket tool, right? So say you're given like a picture. If you click a paint bucket tool and you click on the picture on a specific pixel, what happens? Say like you have like a red pixel and then you click blue on the paint bucket. What happens to like the red pixels around it? Everything turns blue. So if it's the same pixel, it'll turn blue as well, that exact same color. Does that make sense? That's what we're trying to do. That's what we're creating. We're creating an algorithm where given a paint bucket tool, you click on a pixel, it'll explode up and fill that exact color. All right, that's the algorithm. That's flood fill. Basically, the generic thing is just saying you're given an n by n grid, right? So your pixels are n by n sized, called image, where image ij is the pixel value. Basically, pixel could be value 5, and if you click on that pixel that's the value of 5, all the surrounding pixels adjacency up, down, left, right will become say 7 or whatever your target is, right? You're given 3 integers, SR, SC, and color. Your task is to perform a flood fill from SRSC. That's like source row, source column, basically. So basically what you're saying is I click on this pixel, and from there, fill it. And what happens, right? And your goal is to just return that matrix filled up. Make sense? Any questions on that? So input is given as a 2D array like this, right? And there's outputs here. Let me kind of like copy this picture and then just kind of show you here. So here's the picture, right? Let me just kind of zoom in here. All right. So our source was over here, right? So let's kind of see what we do here. So this is another type of graph. It's a matrix. It's not a JSON list. It's not any of that. This is the other most common type of graph you're going to encounter. You're going to go perform a flood fill from this. So any ones that are adjacent to this, kind of going to explode like a chain reaction. So 1 will go here. This will become, so first this becomes 2, right? So it becomes 2 here. It goes here. It goes here. Goes here. Goes here. Tries to go here, but it's base case, right? It's out of bounds. Tries to go here, but base case out of bounds. Tries to go here, here, here. We can't, right? It's out of bounds. So in the end, all we've been able to do is the stuff that I highlighted. This one does not get touched because we can only do up, down, left, right. So if we go down, it's a 0, we can't go forward. We go right, it's a 0, we can't go forward, so therefore we can't touch this one. So when you look at the solution, you see over here, all of them are true now except for the 1, and the 0 is obviously kind of like a wall. Everyone understand the solution? Okay, so let's talk about how we can actually solve this. So basically, the way you solve this What do you think we're going to use? What are you doing for graph problems? What's like every algorithm that we use for graphs? The answer is what? We just talked about. I just told you the two different. What are the two different algorithms we've been talking about this whole time? Matt, BFS or DFS? Which one? Why? What? So you don't, so you think BFS? Final answer? Exactly. You can do either. Why? Why can you do either? Are we looking at shortest path? No. Are we looking at the number of paths or whatever? No. What are we trying to do? Just go as far as we can, right? Expand as far as we can. So what does that mean? It doesn't matter. You can do whichever one you want. So that's the thing, right? You have to kind of figure out these things. If like, do I like start thinking, do I need to choose this? Do I choose that? Or choose the one that you're most comfortable with? Um, I just like BFS iteratively for some reason. It's like my favorite algorithm. So I just do BFS. But you could do both. I think in my solution I have all three. So I'm going to show you that as well. So basically the way it would work, right? DFS is you're going to go up, down, left, right, or any combination of the cardinal directions, up, down, left, right. And you're going to keep searching and go deep. So let's say we start from here, let's do up as like a priority, right? Up, down, left, right as a priority. So we still go from here, 1, 1, right? And now we're going to go up again, out of bounds, right? Down is already visited, so we don't go there. Visit set, right? Left, we're going to go here. Don't forget about the right, recursively or iteratively. Now we're here. Up, out of bounds. Down, let's keep going. Up, we've done. Down, we go. Then up, we've done. Down, out of bounds. Left, out of bounds. Right, out of bounds. So at this point, we've gone depth first into this path. Now we're going to go back up, right? So we've done down, we've done left, out of bounds, right visited. Here, left, out of bounds, right visited. We return here. So now we're at this case. Go right, and then up, down, out of bounds, visited, out of bounds. All right, that's DFS. I kind of showed you the exact path that we're doing. Does anyone have any questions on DFS? So this recursive and iterative, both ways are using a stack, so it's the same exact solution. That's how the path would look. You're going to go just as far as you want, all the way down here, right? And then you're going to go here. BFS, start here, right? And then we're going to go add this, Just going to do it all at once. Going to go here, here, right? These two things are going to be touched at the same time. And then this, and this can be touched at the same time. And then out of bounds are all going to be done. Out of bounds at the same exact step. And then we're done. So you can kind of think of it, I think of it like a wave. Wave 1, right? Wave 2. And then like wave 3, which encompasses the rest of it, right? DFS. And what's our exit condition? Once we have nothing else to traverse. When there's no more valid ones that we can add to our queue or stack, because 0 or out of bounds or edge is our base case, then we're done. At that point, we return the image. Make sense? Any questions on the kind of theoretical solution to this problem? No? So let's just show you the code. So this one's a little bit longer, so I'm going to show it because I don't want to mess this up live. And then you all think I'm a sham and don't deserve my job. So here is the code. And this actually, I think let me see. Yeah, I have the DFS as well version here. So I did BFS again because I don't know. I just like BFS. But let's talk about it. So this matrix problem will have a lot more boilerplate. So these problems are a lot more full of text and full of code, and it's like 30 lines and like, oh my God, right? Like you'll be fine. It's all I did here was I had a constant rows that tells me how long the rows are, just to make it easier for myself, and how long the columns are, right? You don't have to do this. I just do it because it's easier for me to kind of remember. Original color, I'm just saying is image srst to kind of just give myself some more variables so I can turn this into more English pseudocode just to help yourself. Don't be afraid of adding more variables that make things easier for your life. Because if I have to do all of this stuff, I'm going to go crazy. I'm going to lose something. So keep it simple and use real English words for your variables so you kind of remember. Visit set, obviously, right? Then it's just the basics. Queue. We have our queue, and in our queue, we're going to have a tuple of our x and y coordinates. In this case, because remember, we have an x and y, so this would be x would be 1, y would be 1. 1, 1, 0, 1, right? You know, like rows and columns, right? So our queue will be x and y coordinates as a tuple. So while queue, We're going to pop the row and the column from our queue, right? And then here is our kind of base case. If row is less than 0 or r equals rows, or if c is less than 0 or c is equal to columns, or the current pixel, the current location is not equal to the original color, or if the row and column are invisibly. That's a lot. So actually, you can even simplify this in Python, but I wanted to give you like the whole thing. Basically, it's saying over here, if row or column is out of bounds, right? If it's less than 0 here, this is out of bounds. If it's equal to length of rows, so rows, say rows is 3, well, arrays are 0, index would be 0, 1, 2. Index 3 is out of bounds. So is index 3 or index 0 out of bounds? Make sense? So likewise here, index 0, index 3 out of bounds in this case. But it would be n by n. That's why I have the rows and the columns, because it could be a rectangle as well. Right? Any questions about that base case? No? Good. If you want to do something simpler, you can do something like this. If r not in range of rows, or c not in range of columns, that's another way of doing it. Basically, that's the exact same thing as saying less than 0 or greater. So I just did this way because I think it's less text and more Englishy, right? So that's our first base case. Or second base case, if our current coordinate is not equal to original color. So say that we were here and this was like a 3, right? Or this is a 3. We started at 1, so 1 is the color that we're changing. We can't just change every color and just turn the whole image blue, right? If we're just clicking on a green color, only the green colors that are adjacent will become blue, right? You don't, like, say you have a circle and you want to color the circle, it should still have the black outline of the circle, right? So that's what we're doing here. So that's our second base case. If the current pixel is not equal to the original color. Any questions on that? Okay, and the last one should be pretty easy. If this coordinate is not in our visited set. So as long as we haven't seen it yet, we're good to go. But if we have done any of these things, out of bounds, not the right color, or visited, we continue, we skip that. Okay? Basic is good? Cool. Okay, next step. Obviously, change the color. So we're going to change the color to that color that we're changing it to, and we're going to add that row and column to our visited, saying we've already officially changed this color. And then this is the fun part, right? We're just going to append to our queue, row -1, row +1, column -1, column +1. This thing up, down, left, right. Pretty simple, right? And then return the image when you're done. And that's the whole algorithm. Biggest thing is that you have to remember more base cases, because you will be out of bounds. In the JCC list, you don't go out of bounds just because you build it yourself. So that's an extra base case. And also, instead of saying like for neighbor in a JCC list, append it, you have to manually go up, down, left, right. Or you can use a for loop with like the new column, new row. It's like a different way of doing it. You can just Google it, but I just find it simpler to just say up, down, left, right. It's a lot of copy and pasting, but no one's going to sue you if you do it this way. But there's like another way of doing it where you like create like a list and like, but I feel like that's way too much work just to up, down, left, right. All right, and then just for reference, for DFS, it's commented out, but so the colors are kind of weird. But basically, it's saying, right, if it's out of bounds, you return rather than continue. You don't have to do the pop left. You don't have to do this, the queue append. It does it for you. So you change the color, visit.add, and just DFS up, down, left, right, and then you return it, right? And you have to call DFS in the beginning and return the image, right? Any questions on matrices? No? Cool. So I'm going to kind of give you, this isn't a problem that you can do on your own. This was actually one of my interview questions as well. Google, like a similar variation of this. Graph valid tree is a premium problem, but I'm pretty sure you can find it online for free somewhere else. I recommend doing this one because it kind of combines trees with graphs and kind of makes you think of both. So I recommend doing that. But just to summarize, right? Just because we're out of time. Basically, a JCC list are your bread and butter. You do DFS and BFS. Look like this when you draw them out. DFS, BFS, I've showed you in the code, and I showed again if you want to take a picture later. And it looks like this. It's a hash map with vertices being as the key and the value as a list. Or it could be lists of edges, which I showed you as well before, right? Which just means you have to kind of do something like this and make your own JCC list, and it will look like the original, right? Cool. And then the second one is just a matrix, which is a 2D array, and with that, it's just up, down, left, right, rather than that. Right, and with that, you should know enough to do a ton of graph problems. So if you go into LeetCode.io, it's my favorite website in the world. If you go to graphs, there's a ton of graph problems, and so I did so many that are not even here. Like number of islands, max out of islands, clone graphs. Like for example, number of islands. Just spoiler alert. Um, Same thing. You just do DFS or BFS. Like oh here, look, I even did DFS. I did BFS, and I put both things in my thing. And again, look, it's while Q pop left, base case out of bounds, right? Or it's not valid, or it's visited continue, or it's up down left right. Same exact solution. The only thing is that instead of that, I'm doing a nested for loop and just counting number of islands, right? Same exact algorithm. Um, Rotting oranges is also a really fun one. There's some really funny graph problems out there, where you, again, wild Q, pop left. Oh, look at that, up, down, left, right. We added some more like if stuff because it's based on the question. If it's not, if it's out of bounds or it's invisible, you don't do it. Right? Same exact thing, just changing a little bit depending on like, all right, how does this question affect my algorithm? So I have my template memorized. How does this question change my template to fit the answer? That's all you gotta do. And then like another one like I just did like bombs detonating. It's like a really random, like they have the funniest names for graph problems. So here's like a list of bombs, right? And whatever, had to do some math because this is a directed graph. But then here, look, BFS, Q, visited, while Q, pop left for neighbor and adjacent. If not a visit, do this, return length of visited. Boom, right? Same exact thing. So once you understand, also here's an example of like the adjacency list. I have to build it myself. But like this was just like more mathy stuff. But basically, right, it's all the same exact thing, just a different kind of application of that algorithm. And again, if you want to take a picture of this, this is like the template, like the most basic version of DFS and BFS they can really give you. This is, I would recommend take a picture of that. Do this problem on LeetCode like 10 times. Do it like every day until you memorize it, and then do more problems. Because this is like the easiest JCC list problem I can give you. It's not even on the LeetCode list, but it's like it's great. And then flood fill, all you have to just know like it's up, down, left, and right. I recommend doing this as well. This is a really good first problem for you to do matrices on, and do it again. Do it recursively DFS, do it iterative DFS, and do it BFS. Do it multiple times. Do it like every other day, because if you do it that way, you'll get more practice and you'll memorize it, and you're good to go. Um, and with that, do all of these problems you can. They're all very similar, so it's not that hard. They're just lots of text. And if you do this, you can get a FANG job. I'm not even kidding. I've only and like I'm not a LeetCode fanatic, so just to tell you, like it is completely realistic and doable for many of you to do as well. I've only done 190 LeetCode in my whole life. Like I haven't done that many, and almost all of them were in September and October when I was interviewing for Google. So I only had 3 4 weeks of study, and look, if you look at my history, Google hit me up here, right? I hadn't done any LeetCode for a whole year, so I was panicking, like, holy moly, I'm gonna fail and not get this job. And then look at me, I'm sorry, in 2 weeks. So it's like you can do this if you really dedicate your time. Study. It's not like crazy. Do a couple a day, but if I can make it in 100, and actually I only had 150 by the time I did my interviews. I did 40 extra because I thought I was going to get rejected, so I was applying to more jobs. But I did it with 150. So you don't need to do a lot of LeetCode to get a job at FANG. So, but I do recommend you really master graphs, because 5 out of 5 of my tech interviews there were graphs. There were two. There was one tree problem, two JCC list problems, a trie, which is a different data structure, which is an n-ary tree. Um, I think a matrix problem. But yeah, flood fill. And then I had one more, I don't remember. But either way, it was all graphs, right? So practice this, and you might actually be able to get a job at FANG. I'm not even kidding. I did 150, right? The only thing is that you need to apply. Just again, it's a heads up. Meta is hiring right now, so you want to apply to Meta, right? Meta Go and Meta Careers. They're another FANG. They have jobs there right now. So just go on there, look at their openings. I think it's up at least for a couple of weeks. If you want to apply, as a guy called CRVRVE Curve. He has like a GitHub repository of new grad positions. And if you go there, look who's hiring. Almost the entire country. Oh, look, Apple's hiring. You want to go to Cupertino? Like, apply to Apple. These are all new grad listings, and they have also internships as well. So apply to everything. Salesforce is hiring. They're a really good like FANG adjacent. NVIDIA, the best company in the world. If you go work there, you're going to be a millionaire, right? Do graphs, and you'll get a job there. But that's it for me because I'm retiring after 2 weeks from now. So if you want to find me, I'll be up in Boston doing stuff, software engineering stuff. But yeah, any other questions before we stop? Well, that's it. Then enjoy your snacks. Thank you. Oh yeah, let me. Thank you, thank you. Let me also just give you a feedback before you leave because we need to do this for learning comments. Um, Here you go. Before you leave, just fill out a feedback form because even though I'm going to be riding off into the sunset, I have a friend who's going to take over for me. I don't know if you guys have heard of Andrew Martin, A Mart on Discord. He's going to be my replacement. And he's beautiful. I love that guy. So come support A Mart when he takes over my place for these workshops. He's also need the feedback form so we can continue yes. Workshops like this. Because if we don't have feedback, then they're not going to have the budget and they're not going to pay people to do it, and then you won't have workshops. So hopefully you learn a lot from this because I wish I had this when I was learning. So I just tried my best to give you guys what as much as I can in like the 1 hour that we have. So yeah, just do this, and then LeetCode. Please do this. It's great. You don't even have to look. I didn't even do any of the bottom stuff. I ignored it completely. And that's still fine. But graphs are great. DP, backtracking, and apply to jobs. Even if you don't think you're going to get in, best advice I can say is try. I applied to Google thinking, oh yeah, what's the worst that can happen? Right, I'll get rejected. And then I didn't take my first screening seriously, and I somehow didn't fail, even though I didn't study at all. They gave me a second tech screen, and I'm like, oh, I guess I actually have a chance. And then I just did like 6, 8 hours a day of LeetCode. And then on tests were like, I had like 3 weeks to prepare. Every day I'm just like, it's either this or I'm not going to have any job again, and I'm stuck at square one. So if you get that opportunity, which is just random RNG, I have no clue how I got my interview, but if you get lucky and you get an interview, make sure that you can convert that into the offer, because that's the only thing stopping you is yourself. That's why I tell everyone, like, nothing's stopping you except for yourself at that point. It's a skill issue. Don't be that. Don't be the skill issue person. Be the one who sets the skill. But yeah, once you're done, you guys can leave. By the way, we're good to go. And if you ever need tutoring, go to Learning Commons. Websites qclc.wcmy online right over here. Book tutoring appointments. We tutor all classes